Okay, the title of this talk is Physical Understanding of the Tropical Cyclone Wind Pressure Relationship. My name is Dan Chavas. I'm an assistant professor of atmospheric science at Purdue in the Department of Earth, Atmosphere, and Planetary Sciences. This is a talk that's very similar to one I gave in April 2018 at the AMS Hurricanes and Tropical Meteorology Conference. This is work done in collaboration with Chavas Reed, a professor at Stony Brook, and John Knaff at Colorado State and NOAA. And this work was published in 2017 in a Nature Communications paper, so I encourage you to check that out or visit my website. The full citation is provided at the end of this presentation. Having two metrics for tropical cyclone intensity can cause problems. One canonical example of this is Hurricane Sandy in 2012, which caused a lot of damage, as is well known in the Northeast, particularly around New York. And its intensity prior to landfall in terms of its maximum wind speed was 75 knots, which was barely a Category 1. I think there's some debate even about that. And of course, it was starting to undergo extratropical transition. But its minimum central pressure, surface pressure, was 943 hectopascals, which is typical of a Category 3 or 4 storm. So really the question is, how are we supposed to interpret this? This is clearly quite conflicting information in terms of if you're thinking about risk. So empirically, it's been known for some time that the central pressure deficit increases primarily with the maximum wind speed and secondarily with latitude and size. And so it's shown on the left here is a kind of a canonical wind pressure relationship from Knaff and Zaire 2007, showing maximum wind speed on the x-axis in knots and minimum sea level pressure in hectopascals on the y-axis. Where we, as is expected, you expect that that as maximum wind speed increases, the minimum central pressure decreases. And so similarly, Knaff and Zaire in 07 showed that as you go to higher latitude, the central pressure deficit tends to increase. And then, so it gets to be more negative here, these dots shifting downward as you go to higher latitude. And similarly, as you go to a larger size, these dots go from towards larger size, these dots shift downward, again indicating a larger central pressure deficit. And so this is fine. We've understood this empirically, but we actually don't have a good physical understanding of this empirical relationship. So that's what we're after. So we can start from simple, good old gradient wind balance, which is actually what Knaff and Zaire 2007 lead off with as the motivation for their work, but they just didn't really go into it in much greater detail theoretically. From gradient wind balance, it relates the radial distribution of tangential wind and pressure. And so that's shown here in the equation at the top. And so given the complete radial structure of the wind field, this equation can be integrated to yield a physical prediction for the central pressure deficit. And so I just jumped to that solution here. You can read this, go through this in the paper as well. But you can phrase this in non-dimensional terms, and what pops out is you need the solution for the radial structure of angular momentum, absolute angular momentum, which is this capital M, and then in this non-dimensional form, you end up with a single non-dimensional parameter, which has in the numerator the dominant term is this a velocity scale given by half the product of the Coriolis parameter and the overall size of the storm. And so that former part, the angular momentum structure, we actually now have a two-region model for the complete storm structure of wind speed, and that's actually phrased in terms of absolute angular momentum. And so this is from Chavas et al. 2015 and Chavas and Lin 2016. That's shown in red as the absolute angular momentum, and this is just shown schematically here. It had no analytical solution, but what was interesting is its principal underlying parameters is the maximum wind speed, Vmax, and then this same velocity scale that I just mentioned a moment ago, 1/2 f r naught, also shows up as the second. So what's remarkable is that if you combine these two pieces of information, you can actually show analytically a prediction that the central pressure deficit should depend principally on the maximum wind speed and this velocity scale 1/2 f r naught. And this comes out of the non-dimensional angular momentum form shown before. And so again, there's not an analytical solution because we don't have one for the angular momentum profile itself, but you can deduce mathematically what these dominant parameters are. And so just on the right here is just an example, a particularly good example, of course, showing the wind structure from the model as compared to observations from Katrina. And so in our case, this outer radius is always a little bit difficult to estimate directly from observations. It can be noisy, and so here we really want to measure the size of the outer circulation, the overall size of the storm. And so here we're using the radius of 8 meters per second to be well above the noise, but still well outside the inner convecting core of the storm. Okay, so we have a couple of theoretical questions we like to test. So first and foremost is actually a simple or intermediate step is, can we predict the central pressure deficit from the full wind profile just using gradient wind balance? So forgetting all the theory we just talked about, just go to gradient wind balance itself and integrate it. How well does that work? And can we then secondarily predict the central pressure deficit much more simply using just two parameters, which is the maximum wind speed, and then we're going to use this 1/2 FR8 as our velocity scale that we get from theory. And so we'd like to test this really comprehensively, so not just in a simple fashion, but across a hierarchy of models using the parlance from HELD 2005. And we're going to use as our experimental laboratory CAM, Community Atmosphere Model version 5.3, doing experiments with quite high climate model resolution of about 25 kilometers horizontally. That's approximately uniform globally. Okay, so we start off with a simulation that we'll just call Omega here, which is an aquaplanet with uniform thermal forcing under the parlance of Merlis et al. In 2016. This has also been analyzed in recent papers in 2019 by our group. And so we set the sea surface temperature to be 29 degrees Celsius, and that's constant uniform everywhere. The solar insolation is 340 watts per meter squared, a diurnal mean that's uniform everywhere. So we're really removing the thermodynamic variability in the system. And also, again, the surface is just water covered everywhere. And so what you get is something pretty remarkable and very different from the real world, which is one where we've removed the thermodynamic forcing for the jet stream and for really most horizontal variability in the system. And what you end up with is a world that's largely just covered in tropical cyclones. So that's what you're seeing here is the near surface wind speeds are colored here. The black line is 12 meter per second wind speed. And you get these tropical cyclones that form, they actually still form at low latitudes as they do in the real world, and they move poleward and westward. You can track them by eye. And instead of running into the jet stream or running over land or cold water, they just sort of pile up at high latitudes. And so what's really nice statistically is this gives us lots and lots of hurricanes, which is the phenomenon that we are interested in. So the experimental utility here is we end up with predominantly hurricanes which have time-varying values of maximum wind speed, Vmax of size, actually storm size varies quite a bit, so the radius of 8 meters per second, and F, our Coriolis parameter, these storms span a range of latitudes. But the environment is homogeneous, so this is kind of our simplest model for testing our hypotheses in our hierarchy. Next on the rung is an AMIP-like, Earth-like historical simulation for the period 1979 to 2012, where we use sea surface temperatures and solar insolation from the historical period. And so this, again, is the near-surface wind speed shown in colors. And so now we have a much richer heterogeneity of circulations associated with, say, at mid-latitudes. You can clearly see extratropical cyclone activity, particularly in the southern hemisphere. But you still do get, among other things, tropical cyclones forming at low latitudes in the basins where you expect them to form. So generally, this gives you a climatology that's broadly reasonable in terms of tropical cyclones in an Earth-like present-day climate. So here, this is our next rung where we have our same variable tropical cyclones as before, but now we've introduced substantial environmental heterogeneity akin to that found in the present-day Earth. Okay, so first up, we can look at, just as an example track from our Omega simulation, our aquaplanet simulation. This is, in the top left, is showing the tangential wind profiles taken from the lowest model level of storms, going from blue to red in order of time during the life cycle of the storm. And the dots indicate the radius of 8 meters per second here, so you can see this pretty substantial variability in storm size. And so what we do is we take those wind profiles and we actually rescale them by a single constant across all storms in the simulation. And so this is in some sense a reverse boundary layer wind speed reduction factor, if you want to think of it that way. Just keeping things very simple, so we rescale by values that are pretty similar between the two simulations. And so we take those profiles and then we integrate inwards from the outer radius, which is marked here in these the hollow circles on the left, into the center, and that gives us a central pressure deficit calculation as predicted from gradient wind balance, and that's on the y-axis in hectopascals. And on the x-axis is that given from actually calculated as the difference in pressure from the storms at each time step in CAM 5, so prediction versus truth. And you can see this just really does a quite remarkable job of capturing that variability here. Okay, so now we can take so that's just one track. We can now accumulate statistics across all the tracks in our system and put them all into one single plot, essentially, and evaluate this, how well gradient wind balance performs statistically. And so it's shown here on the x-axis, again, is the central pressure deficit from the model itself, and the y-axis is that predicted by gradient wind balance. And so I'm going to show similar plots like this over and over again. So the colors denote the relative frequency, so you can get a sense of where the data exists in this. And then within here, we've plotted the solid line in dots is the median, the conditional median within each central pressure deficit bin, and then there's the interquartile and 5 to 95 percentile range. So it gives you a sense of any conditional bias in the system. And so on the left is for omega, and on the right is for AMIP, and I've just highlighted the R squared value in red on each side. It's really the one I'm going to focus on here. What you can see is that does a remarkably good job in both cases, gradient wind balance. You get 97% of the variance explained in omega, 94% in AMIP, which is not surprising. The real world is a little bit more complicated, but even then, it's doing a remarkably good job. So the second question then is, given that we know the gradient wind balance itself does work, can we predict the central pressure deficit more simply from our two simple parameters given to us by theory? So really what we're saying is, could we get by with a lot less information? So the gradient wind balance calculation, you need the entire wind profile, which we really don't have in observations almost ever. And so a lot less information would be really nice here. So what we'd like to do is just simple multiple linear regression on our two velocity scales, Vmax and 1/2 FR8. Okay, now we'd like to do the same thing we did before, but now testing our theory using simple multiple linear regression. So the equation is shown in the bottom right. Again, omega's on the left, AMIP's on the right, and I've left in black the original explained variance, the R squared values for each of them. And so you can see when we do this simple multiple linear regression, we're still explaining nearly all of the variance, and 94% in terms of omega and 95% in terms of AMIP, which is pretty remarkable. There's a little bit of conditional bias at very high central pressure deficits, but overall it's still doing. So we can actually go one step further, and since we only have two parameters, rather than trying to use this multiple linear regression model, we can just look directly at the joint dependence of the central pressure deficit on these two parameters. And so it's shown on the left is omega, and middle is AMIP here. And so in the x-axis is our 1/2 FR8 velocity scale, and the y-axis is Vmax, and the colors denote the central pressure deficit, going from the dark blues is a lower central pressure deficit up to the yellows is a higher central pressure deficit. And then the pink lines just give you a sense of the sample size of events in these distributions. And so what you can see is that there's clearly much stronger dependence of the central pressure deficit on the maximum wind speed, and then a weaker secondary dependence on 1/2 FR8 increases as you go towards higher values of either of these parameters. And that character is very similar when you compare between the omega simulation or aquaplanet and our AMIP historical simulation. So you'll notice that the AMIP actually spans a larger region of a slightly larger region of values, particularly towards higher values of 1/2 FR8, indicating which may indicate something about the behavior of the system in the much more complicated real world. But overall, the character is remarkably similar. These dependencies are really similar, despite the fact that these worlds are wildly different from each other. So again, we're really highlighting something that seems to be pretty fundamental to the behavior of hurricanes that doesn't depend on, say, the wide range of external variability that you get in the real world. So we can go one final step beyond this is to include an observational analysis. So we do an updated version of the Knaff Air 2007 methodology using aircraft data. And so we can bin it here, and so we have much less data here. We're really confined to storms that have aircraft observations, largely in the western Atlantic Ocean. And so what you end up with is much weaker coverage or much sparser coverage of the phase space, but you can still pick out the overall character, a very similar empirical dependence as is found in the simulations. And so one really interesting note is there's this little arm that sticks out to the right in the observations where you see the colors getting approaching bluer and then greener colors as you go towards the right. So the maximum wind speed is not increasing much, but the FR8 is getting larger, and this is actually associated with Sandy itself. And so Sandy was moving poleward and getting larger rapidly, and so this little arm actually, you can see Sandy in this phase space, which is pretty remarkable. Okay, so just to summarize, it's really looking at physical understanding of the tropical cyclone wind pressure relationship. So the key results is the central pressure deficit is really a combined measure of the maximum wind speed and the product of storm size and the Coriolis parameter. So really giving some strong physical foundation, theoretical foundation to past empirical work. I just want to highlight the design of this is really taking a hierarchy of models approach to try to bridge the gap between a reduced complexity world, this aquaplanet world, and the real Earth, both real Earth simulated in a climate model as well as observations. A couple of notes is that the minimum central pressure is known to better predict historical economic damages from hurricanes better than the maximum wind speed, and there's actually now a paper that I'd like to emphasize that'll be coming out in 2020 in BAMS from Phil Klotzbach, taking this another step. And just note that small-scale intercore variability, such as eye wall replacement cycles, are likely poorly captured here. And in general, just very small storms are not going to be reproduced with these climate models. So that's just something to be aware of. So again, this has been published in, this was in 2017 in Nature Communications. I recommend you check it out if you're interested. So thanks very much.